Okay. All right, let's talk about one more force. In some ways it's an easy force, but people do make mistakes, so let's just talk about this a bit. It's the tension force. Okay? So we're talking about types of force right now, and we need to study those forces and think about what determines the strength of the force, which is also called the force magnitude, and the direction. So that's what we've been studying. Once we look at each individual force, we can look at an object and look at all the forces on it, normal forces, etc., and put it into our method. So when it comes to tension, it's usually from a rope or a string. We just use Ft or capital T, which can be confused with the period of time, so you have to know the context. This would be in newtons or pounds, right? If there are two strings, it can be difficult to identify. There's tension from string 1 and tension from string 2. I don't like to use T1 and T2 too much because I like to use the subscript 1, 2, 3, 4 for time sequence. So I kind of prefer tension from string A and tension from string B. It doesn't really matter so much, but be careful. You can see that the notation gets clunky, but it does get important. If you have the same string, we're going to talk about, for now, we're going to have the same tension all along the string. It's not entirely true. So we're just going to throw it in there. There's no equation for the tension. Tension is always a pull along the line of the string or rope. But we aren't caring about the string of the rope. Usually, in upper division, you can actually look at that. But it's a pull on our object. So in this case, I've got an object hanging here, and it's got two different strings on it. So the only thing touching this object, if this is my receiver, is the string on your right and the string on your left here. Two different strings. So I've clearly got a tension as a pull along that line and a pull along this line. And then, of course, there's the non-contact force of gravity and the non-contact force of gravity from me on it, which is completely unmeasurable, so we don't worry about it. Right? So that's all we do. We put it in. Let's draw a free body diagram for this case. So we draw this picture, and we've got an attachment here, and we've got the object hanging here. And we've got two ropes, and you could identify it however. If you got colors, use them. It's kind of nice. I've got the purple rope, and I've got the green rope. And there could be different angles, right? And usually when we're dealing with cases like this, it makes sense to use a coordinate system of vertical and horizontal, or vertically down and horizontal, but not always. So it just depends on the context. We'll see. So we want to draw a free body diagram for our object that's hanging there. And one mistake people make is they take the tension force, the strength of the pull, as related to the length. And you don't do that. Because when I draw a force vector, the length is just a visual representation of the strength. And so I really encourage, and even some books, they'll put the tension vector on this here, and I encourage you not to do that. Now what is true, it is along the line of the rope. So I'm going to call this TA, or TP for purple. I could do that too, right? TA. Again, personally, I don't put a vector on top of it because the direction is there. This is the strength, and along that whole line I've got the same strength, the same variable in the equation. It really makes things a little clearer and avoids mistakes that I see all the time. What you can say, though, since it's along the rope, is that that force has a direction that is the same as the rope. So you can still use the geometry of the triangle of the rope using rope lengths. So that might be given to you, and that can give you the angles. But force is force, and length is length. Very different things, right? So then over here, and you might try to guess which is stronger, but I've got a TA here and a TB here. So, you know, if it's really obvious, then you might think, okay, which one's going to be stronger? I know one thing that here, when I look at this picture, moving on. Let me go ahead and throw my other force in here, namely the force of gravity, which does have an equation. So notice that the force of gravity is the mass of the receiver times this g. Is the acceleration g? In this case, what's the acceleration? The acceleration of r.
It's
Look at it.
0.
0, I hope. It didn't fall. Okay, good. So it's 0. So this is not the acceleration. This is the force of gravity. And you've seen that two ways on the videos. So that is the strength of the force of gravity no matter what. It's vertically down. All right, so I know that this is a case of static, not moving, v equal to 0, equilibrium. A equal to 0. If A is 0, then force net is equal to 0. And I can do it by components as well. And since this is 2D, I will do it by components. So visually, I can say this force must be balanced by the vertical components of these two forces. And so I simply do not shortcut. So if you follow the steps, you'll be able to do the steps more rapidly, and it will start feeling easy. And don't worry about that. That's actually right. At some point it gets easy. You just look at the object, draw in the forces, choose your coordinates, add up the forces in the x, they equal max, in this case 0. Add up the forces in the y, that equal may, in this case 0. So that means that the x component of the purple, TA, and the x component of the green have to balance the force of gravity. And I don't know which is stronger, really. So it depends on the angles. I'd like to do the little dash there. B, oops, I said X, didn't I? You guys caught that. TBY, TAY, the Y components balance. I guess I could call vertical X. And now in this case, I've got TBX, and that's got to be the same length or balance as TAX. So don't skip, put them in the table, and whatever you're given some things, you find other things. But don't draw the tension as the length. That's one big thing. It's always a pull. So now if I take a rope and I try to push on Alejandro or Gary, I'm not doing very good pushing, right? But I can pull. Now this is an interesting thing here too. When you pull, okay, it depends on who you want to look at. I can go like this. Now watch this. Notice that I can make this side tight and this side loose. So in the same rope, the tension isn't always the same. And if you have a lot of friction, you might have that dragging along there, so it's loose on one side. For our models, as an introduction, we deal with cases like this, and then the tension will be considered the same. Our pulleys that we use will be considered low mass, low friction, negligible mass, negligible friction pulleys. And in that case, we can say the tension strength on either side is the same. However, the tension direction is different. So if I put a mass over here and a mass, same mass over here, they should balance. And so here the tensions are the same in strength, but not in direction around the pulley. We're going to get to pulleys later. We'll get to the effective pulleys, okay? Here they're both up. Suppose, this gets a little tricky. So for now, the tension on one side is the same strength as the tension on the other. Here, this mass gets pulled up. Here, this mass gets pulled up. The rope or string gets pulled down, but I don't care about it. The string gets pulled down over here. I don't care about it. The pulley is there, but I'm not going to care about it. If I load up more mass, I get interesting things happening. Well, you know what's going to happen. It's going to go pretty fast, right? So in that case, I've got the case of acceleration. So I can have no acceleration, or I can have an acceleration. That's going to be a bit much on that guy. So let's do this and take a look at it on the board. Here's static equilibrium. If they're different ropes or strings, they're different tension. I don't care what happens to Alejandro. I just care what happens to me. I don't care what happens to Gary. It just happened to me. We're not going to deal with cases where the tension is different on two different sides. Okay. So when we deal with acceleration, there's something really subtle here. And good exam questions, super quick understanding, can be checked by this question. For example, I have a pulley, which we draw like that. I have some block A. I have some block B. Which one has more mass? You probably guessed wrong, because you can't read my mind. That's made out of a lightweight wood or cotton, and this is made out of steel. So don't necessarily guess. Usually when people draw it, they're implying more mass, but more volume doesn't mean more mass. Which way is it going? I don't know. It could be going, it's a static picture. You have to tell me about that. So in that case, I don't know which way it's going. But I do know this. In my model, later we'll see it's different, the tension on both sides. But in my model, I can look at A and say it's got a force of tension. There's only one string, so I just call it T, or Ft. And then it's got a force of what? Gravity, mg. Now if I draw this, mag, which way will that accelerate? This is longer than this, it'll accelerate up. Now that doesn't mean you're not moving down. You could be moving down and slowing down, stop, move up and speed up, right? You can push it down and go. So that's the thing, like with the elevator problem that you saw in the video. So that means that on the same thing, I've got the same amount of tension. Now this is going to be kind of cool. There's the tension over there. Then there's a force of gravity. How strong is the force of gravity? Well, it's mp. If that accelerates up, this I know accelerates down. So that means that the force downward has to be stronger than the force upward. So this must mean that mbg is stronger. And yes, in this case, maybe they're both made out of the same material. Namely, in this case, the one that's bigger will have more mass. But not necessarily, so be careful. So the interesting thing here in dealing with this is I can treat this, and that's a pretty easy problem. But I've drawn my free body diagrams keeping the same T, because then in my algebra, that T, when I get it in one equation, it's the same as the other, so I can solve for T in one, substitute it for the T in the other. I would not put the arrow in there, because that can get pretty confusing. Namely, maybe I should use T is this way, and T is this way. If you put the vectors, then you've got directional things. I just want to know, when I set up my equations, T is the strength, and that's what I'll solve for. I can see the direction. So the last little bit here is, how are we doing? So the key idea working with tension is, and connected objects, is what direction do I use for my coordinates? And here's a tricky little bit. If I know this accelerates up, then I can call that the plus direction. It's only one-dimensional, so you don't need to name it X or Y. You don't need that name. If you want, go ahead. You can call it Y. If you want, you could say that's Y for the A object, in which case acceleration of A would equal to some A, which is a positive number. This is going to accelerate down. If this accelerates up at 1 meter per second every second, or 1 meter per second squared, 2 miles an hour a second, then this will accelerate down at 1 meter per second squared. And so I want to set up my algebra so if I get a positive value for the acceleration of object, capital A, then that's the same as the amount of B. So it's a clever little tool to call this plus for this guy when you analyze this. And then I'd say, if you want, you can call it YB or just plus. And then the acceleration of B is positive, or I should say that's a positive value. And this is a positive value over here. And so in my algebra, that letter, that variable that I go to solve for is still A. And that's the place that you can easily get tangled up if you don't set it up right. So really quickly, there's my object, there's that. So for A, I would say, okay, I've got T, the sum of the forces on A equals the mass of A times the acceleration of A. In this case, that would be T, which is up, and MAG, where G is not the acceleration, down. And that equals MA times some variable A. Now I go over here for B and I set up that equation. The sum of the forces now on B is the mass of B times the acceleration of B. Keeping this, what I have to say now is that the mass of B is in the positive direction, mass of B times G. The force of gravity is positive here. And then this is negative. But the T is the same, so I can mix these equations algebraically when I solve it. Key is setting them up correctly. And that's equal to MB times A. And the A's are the same, so that's one unknown. I didn't create two unknowns by calling positive up. So 1 meter per second there is negative 1 meter per second here. And I kept the T's the same, so that I've got two equations and two unknowns. I haven't introduced more unknowns by naming the same thing different ways. So the brilliance of having your, if you can figure it out, your coordinates go in the direction of acceleration, it really helps. And you can actually do it, set it up differently. But now I can figure out how strong the tension is, what the acceleration is, or whatever. And then go into kinematics. How far does it go in 3 seconds? Or how long does it take to travel a meter, or 1.5 meters, or 1.3 meters, or whatever it is? How fast is it traveling after 0.67 seconds? Kinematics, just go in there, because the forces are the same, so the acceleration is the same, and we're good. And so, okay, cool. So the one thing that I do want to mention is that in real practice, you have to choose your rope, because there's a point at which your rope, can you see this? There you go. Or a string doesn't hold. So not good, especially if you're towing something, right? Like not good. And these accidents happen on an engineering scale. Usually you over-specify things, right? So this rope, this string has stronger. I can't do that. I can do that. So often ropes and strings are specified by the maximum tension, and that's when they're going to break. So sometimes problems will say, you know, what's the maximum speed it can go, or maximum something, before the rope breaks, and then they tell you what the maximum tension is. So then they've given you the tension value for that condition. This one's, but it's a little stretchy. So the other thing about our ropes is stretchy ropes are weird because I can accelerate the rope itself without accelerating the thing. And so for laboratory experiments, we use rope that has very little elasticity. That's actually important for our results, very important for the results. So the maximum strength of a string or rope and the lack of elasticity is important too. So are we winding down? So winding down, that's good. We'll talk more later.